All right, so looks like we can get started. Unfortunately, I have not had time to grade your exams just yet. I will get it done over the weekend, so we will have that done. But so today we're kind of switching gears, right? Oh, could you close the door for me so I don't get in trouble if someone walks by? So far we've been talking about logic from the perspective of 30 or 40 years ago, right? Designing logic at the gate level, right? Where you take the little IC chip, you throw on a couple of AND gates, you wire them together, and you end up with this big messy breadboard that is very difficult to tell what's happening. So the reality is we don't do a lot of that. It still happens occasionally, but mostly in hobbyist circles, because there are tools that are much more equipped to handle the large, complex digital systems that we use today. I mean, you can imagine trying to build a processor with 100 million transistors or components on it and by hand, right? Even if you could get down to that small of scale, you would never be able to put the time in to assemble it, right? So obviously we want to automate things. So that's where we're going today. I'm going to teach this a little bit different than I have before. I'm recording this lecture and so I can go back and see how it goes, but I'll also post it so it's available to go back and review if you want. So remember, I've talked about this before, where I could have some block of logic, right? I don't necessarily have to tell you what's in here, but I may say something like it's a full adder and it has ports A, B, C in, C out, and sub, right? Now, you don't have to know how they implemented that full adder in order for you to understand what it's doing, right? So you've learned already what full adders do. So I can write this block and you know what those AND and OR gates look like in your head, or at least the function. So then the question becomes, how do I turn this into code, right? You know how to turn something like this into a component on a breadboard, right? Because you could go, well, the description of this is such and such. I'm going to draw it on the truth table, figure out what the logic are, minimize the expression, and ta-da, right? But we need to do this a little bit differently. So I'm going to do this from the perspective of something a little bit different, because your homework is actually going to be, sorry, not your homework, your next lab is to build a 4-bit full adder in VHDL, okay? So initially you were going to have to build a 4-bit full adder on a breadboard, but that really is just a test of your dexterity and organization skills, right? And it takes a very long time to do that, especially when you're new. And I don't see it serving as instructional as let's taking the opportunity to use what we learned with building the initial full adder and turn it into VHDL so that we have a concrete connection between something that you did on the board in the physical world into code. But because we're doing the full adder as a lab, I don't want to give you guys all the answers to that. So I'm going to create a new component. Now, I've mentioned them before. They are called multiplexers. Multiplexers are really quite simple. This is your multiplexer schematic. For your ports, we can call this, say, X, Y, and S. In this case, S is not sum, S is select. Okay? I'm going to call the output port F. Now notice at this point, I'm not labeling the connections to it. I'm labeling inside this block. Just like that full adder block diagram, the ports have a name, okay? Now, there's a couple different ways that you can build circuits in VHDL. The two different ways are structural and behavioral. Now, structural, and you will use both in almost every design you do. So structural simply describes how things are connected together. So like when I drew up this block diagram of the full 4-bit, well, let's just do 2-bit adder for speed, full adder, it has ports that come out. This is, this is CO. And then some would come here and you'd have some bit number right, and then you'd have some 1, CO. Right? So this is a block diagram of a 2-bit adder. These guys are the ports. This is where things come into that logic and out of that logic. Okay. Similar, these are ports, X and Y. Now, I want to create a block that is a 4-bit mux using only 2-bit, 2-input muxes. Okay. So you know how like we've done a 4-input AND gate from 2-input AND gates? We're going to do the same thing, but with muxes. Now, muxes are important. All they do is if the select line is 0, it takes the X inputs. If the select line is 1, it takes the Y inputs, right? This is controlling what we call the data path, which we will get to in more detail later. But basically what that is saying is that I can have one of 2 inputs and we're going to put it to the output. We want to select which input we're putting into the output, right? You can imagine all kinds of reasons we might want to do that, right? A big one is we don't want to do a whole lot of logic. So say you were trying to add 2 different numbers into your full adder on your breadboard. And instead of like wiring up every time, you could wire them up one time, plug them into a mux, and hit a select signal, right? So to visualize that, this would be a full adder, right? I could connect up this input. We'll call the signal little sf, just signal f, okay? So then if I put a value, 1 here and 0 here, if select is 0, it takes the export 1 and puts it on the output. And so I would add 1 to whatever B is, right? So I get to choose my inputs. We get to build like a switching railroad, right? Tell it where the trains go. That's what we're going to build. Now, this mux, then, we do exactly the same kind of thing that we did with the adder, where I take another mux, and it's going to be essentially the same mux, right? And then copy and paste, throw down another one of X, Y, select, F. Okay, now I'm going to go and call these inputs. I'm going to change the name. So I'm going to stick with my ports being named X. And I want to imagine that now I'm going to give you guys this as a big block. Okay, so I'm going to put that guy inside of a block. I haven't used A, B, C, D. Actually, sorry, let me redraw that. That is incorrect. A, C, D. Okay. So, and then this will be S0 and S1. Right, this is the same type of architecture as the adder, but it has these select signals. Now, we'll talk about muxes in a little more detail in an upcoming lecture, but I just want you to get this into your head that the idea, the reason I'm doing this is if this select 0 signal is 0, then X, the A port, this first X, I'm going to call it A, is selected on this mux, and C is selected on this mux, okay? Because S0 is 0. So here and here, I have A and C respectively. And then the second bit, if it's 0, takes A, and if it's at 1, it takes C. Make sense? So we can create a map real quick that just says if my selects are so-and-so, we take A, S0 becomes 1, that means we have B and D, right? This is S0. B, D appear here, 0 at S1 means I take B. There. I have a 4 input mux, right? Or a 4-to-1 mux is another way of saying that. So I can take 4 different inputs. I have 2 bits to select which one of those 4. Ta-da. So how does this relate to VHDL? Well, remember that I said that there are 2 different kinds of structures, we'll call them architectures, that we're going to use in VHDL code. The first is behavioral. It describes how one of these muxes works. Okay? The architecture that is structural, so behavioral is how it works. Structural is how are they connected. Okay, so we're going to build in modules. My mux is going to be one module, and this red box is another module. Okay, I can then, if I wanted, you could quickly imagine if I stick a couple of these in parallel, I can then build an 8 input mux, right? And then there would be a structural description of how those connect. Okay, so what we want to look at then is, I'm going to start off with a bit of a warning, which is I write in what's called pseudocode very often, which pseudocode is I'm going to write in a way that describes what the code is doing more than exact definitions of how you would write the code. Don't worry, we'll go over exact code for it, but I will try and warn you when I will try and inform you which one I'm doing, but be aware that especially if I'm writing code on the board, there's going to be typos, right? Because code editors, if you've ever used one before, you would know that they kind of give you hints as how to fix them. And me, like every other coder in the world, has used it too much as a crutch, and your habits get really bad, okay? So that being said, and you don't have to answer if you don't, well, let me do it the other way. Who amongst you has coded before any language? Okay, you're all in trouble. The more you've done, the worse off you are, because we are not programming a computer language. We are programming circuits. We are describing the way circuits behave. If you write a program in Java, for example, it goes and it starts and it does one line, and then the next line, and then the next line, right? You might get a loop and it loops around. VHDL is the language that we're going to learn. There are others, but VHDL is what we learn. It does not care about the order of statements, right? If I draw up AND gates, and I were to write code for this A, B, C, D, it doesn't go this gate, and then this gate, and then this gate, and this gate. That's not reality, right? They happen all at the same time. They change if I change them close to instantly, right? They have a delay, but close to instantly. So we need a language that reflects that reality. Okay, so if I were to write an AND gate, this is one of the simplest ones. I'm going to use the term F. In VHDL, we use this kind of assignment statement. And I write A and B. This is not pseudocode. This is exactly how I would design an AND gate in VHDL. This is called an assignment statement because I am assigning A and B into F. This is combinational logic, meaning there is no order to it. Okay, there's no memory to it. It just continuously does this. If A or B changes, F will change as quickly as it is physically capable of changing. Okay. If you ever see just a regular equal, for example, this is a question. Is F equal to B? Right? This is an assignment. This is a question. Okay. So we'll get into more specific vocabulary with it, but just remember that in order to assign things, you need to shove it in, right? That's what the direction arrow shows. Okay. Now, let's go ahead and introduce one more type of assignment statement, which we're going to use to make a mux. Muxes are very important and for some reason very confusing in the past when I taught them, so I'm hoping this solves that. Because all the mux does is take two inputs and then a select, and this puts on the output one A or B into the output depending on select. No other logic goes in there. It takes exactly one line of code to make a mux. You just say, what do I call this? Out? Well, let's do F. I wish I hadn't done F. I'm going to erase the AND gate so you don't forget that it's different. Okay. This is now the F of a 2-bit mux. It's assigned to on the port X when S equals 0, else Y. I don't have that on my notes yet. I'm pretty sure this is actual correct Foley code. Okay. What this does is, again, combinational logic, right? So that means there's no memory to it. It happens as quick as it can. When S, this is a conditional. When S is 0, this is the question. Is S equals 0? It will output a 1 or a 0. So really what you end up with is when 0 or when 1. Okay? That's what this is doing. But it's just saying when S is 0. Well, if S is 0, then it's going to put a 1 here and it's true. Therefore, we make the F X. Take whatever is on X and shove it into F, right? However, if this is not 0, we take the otherwise, else, right? And shove Y into F. Now, X and Y in this case are a little confusing because we're going to have two different things going on. Well, three really. We're going to have signals and we're going to have ports. Okay. I have the port X. But now, if I want to connect things together, I need a signal. Okay. So with this signal, earlier I wrote it as SF. I probably want to do something a little more descriptive, and I'm just going to call it M0 for the 0th mux. And this signal I'm going to name M1, okay, for the output. So this signal M0 is attached to F, right? So in order to do this, there's a couple different ways, but this mux doesn't have to know that M0 exists in this architecture yet, okay? There's logic inside of the mux, which is behavioral, which I'm building now. And then there's a structural, which is going to need the M0 to tell that how F is connected to this X, okay? So let's focus for now inside of this mux, okay? This is the only line of code that it takes. And I am saying F, I would really just write F, I just want to be a little clear, right? Because the port I named is F. So my port F is getting assigned to X or Y. Okay. That's all this is doing. Now, in our code, VHDL doesn't know that anything exists, okay? So how do we tell it exists, right? Where do we start? Well, there's this idea of an entity, okay? And you're going to hear me use two words, and I'll come back around, I'll use them all the time. One is entity declaration, and then you'll also hear instantiation, okay? Let's focus on the declaration, which is just declaring to the universe that it exists. More specifically, it's declaring to the software that we use that I exist. So this one is going to be a little bit pseudocoding, but focus on the concept of it. Because the nice thing is a lot of this gets generated for you, which is also why it's going to be bad, because I haven't written this in actual code myself in a very long time. Actually, I should probably pull up an example so I can make sure it's at least close. Okay, so the entity is a keyword. The program will recognize the word entity and realize that you're about to tell it that something exists. I then say the word, or sorry, the name, and I'm just going to call this Max, right? That's its name. The name of the entity is Max, okay? Then I need to tell it what it is. Well, the entity Max is ports, right? The outside world views the Max not through what it does, but through its ports, right? Just like you guys get judged by how you look when you go in for a job interview, this thing gets judged by how it looks to the outside world, okay? So then its ports are going to be X, Y, and F. Now I put them on different lines for a reason. That reason is that there are different types of ports. We have really 3 different types of ports, but let's focus on just 2 for now. The different types of ports are inputs and outputs, right? Inputs like values to be put into them, and will throw an error if you try, well, it would be really weird if you tried to pull a value out of an input. Outputs don't like anything else to drive a signal into it, okay? It's outputting something, it doesn't want something shoved back down its throat, okay? So F is my output, but before I can do that, I need to tell it, well, those are ins. This is an out. Now it knows, okay? The only thing I'm missing here for actual code is there is a colon. All right, then the next thing that we need to do is give it what kind of port is it. So VHDL language we're using is what is called a strongly typed language, which means that I have different types of data that we'll get into later. In this case, it has one value, it is 0 or 1. What is the type of data that we would call this? We've talked about this word a lot, right? What is a 0 or a 1? A bit, right? They're bits. So my type is bit. Now, there's a bit of a, how would I say, complexity in this, because I can perfectly say bit. I can tell you they're bits. Oh, this is a semicolon as well. Okay. And then I have to tell it that I am done with this entity. And I don't say end entity, I say end mux. The mux is done. Notice that most lines in VHDL and in semicolons, that tells it the line is done. Okay. Now, here's the complexity. Bits only take values of 0 or 1, right? But the reality is a little more complicated than that because actual logic can be different things. If you ever didn't plug an input into one of your AND gates and notice that sometimes the value is right and sometimes it's wrong because you don't really know what it is, right? We would call that U. So my bits can be 0, 1, U. I don't know. What if I did one of the other mistakes I've seen you guys make where I have two AND gates and I plug them in together? Well, that output is what we call dual driven because one of them could be trying to make it 0 and one of them is trying to make it a 1, right? In the case of your NAND gates, the 1 is stronger than the 0, so it always is 1. In reality, sometimes they're perfectly matched. We would call that X because we don't know, right? We've used X before as don't cares. This is really we don't know, okay? There are 3 or 5, I forget, other values that this can be that we will get into later. My point is we don't necessarily want a bit because a bit is a poor reflection of the real world, okay? So what we do, instead of telling it bits, I say they are standard logic. Okay, standard logic is basically just a bit, but it can have all of the values that the real world can throw at it. It is a better representation of the real world. Okay, now I know that this entity exists, right? I've told the world I am here. Now we can do things with it. We need to tell it its behavior, right? Because we have to choose structural behavior. Well, inside the MUX needs a behavior. We're not building the top level one yet. Okay, now this one is pretty easy because there's this weird thing where we have ports and we have signals, ports, right? Well, for the sake of inside of the entity, it knows that you're going to need to do something with those ports, otherwise you wouldn't have it, right? So it goes ahead and it creates a signal called X for you. So there is both a signal and a port X that are tied together. They have the same value, so you don't have to worry about connecting them or doing anything. They just exist. Then I need to give it an architecture, which I'm not going to write the whole word out, right? I say there's going to be an architecture of this. Make sure I do this right. Sorry, is it name first or? Yeah, so we give it a name here. Architecture name of MUX is. And then I can give it a begin to let it know that it is starting because there are other things that can happen. Now this name, generally, it will just automatically populate it with its best guess, which is usually behavioral. So the architecture's name is behavioral. Now, weirdly enough, it does not have to be a behavioral thing. This is just a name. So you can give it a description, which can be helpful in later classes. But for now, you can just leave it as whatever you want and just keep in the back of your mind that this is just a name. Okay, so I have architecture behave of the MUX is begin. I take this code, which instead of F2 MUX, right, I just say F because the port is called F. The other ports are X, Y, ooh, see? So this is okay, I forgot my S. S is also standard logic. S. This is actually normal design process. You'll start designing something, realize you're missing something, just go back and add it, everything is fine, right? Now I have the ports that I need. I have X, Y, and S that are inputs. This X, this S, that Y, this code gets inserted in the begin. And then later I would say end behave to let it know that I am done. So this just plugs right into there. I now have a mux. Right? That's all. This is a mux. The outside world doesn't care what this architecture is. It only cares about what this port is. Hopefully you designed inside right so that the word that we name it is descriptive of its function. But the outside world is only going to see its ports. Okay? Now, we can get complicated. But before I do you have any questions? No? Good. Everyone's confident? Or so confused you don't know how to ask questions? Don't worry, I'm so confused because my watch's time is wrong and it keeps drifting. So I have to go exchange my watch, and that's really me and technology are just cursed. What's that? Yeah. So that one is right. My watch is thinking that it is 10:02, and it's done this 3 days in a row now where I've lost an hour and I don't know why. It's really worrying. Okay. Density exists. Let's build up complexity. I want to make that. So unsurprisingly, I need a higher level module. I'm going to call it
You also need your S0 and S1.
Thank you. I'm going to do that a little bit differently, actually, but thanks. Ooh, so here's a fun problem that I just encountered. See how I've named my port out? But out is a reserved word, right? It's a keyword that describes what a port is. So if I did this in actual code, it would be very mad at me. So I need to go back and rethink my design. Perfectly normal. And think of giving a new name. Well, A, B, C, D. I don't want to use F because that's inside right. I actually am allowed to do that, but I strongly advise about using different port names as much as you can so that you don't get stuck and confused. So a descriptive word of this output, then, well, we can simplify it to O. O looks like a 0. That's a terrible idea. X, Y, Z is a terrible one to use. Output could work, but that might be a reserved word by itself. This is the hardest part of designing any big code, is coming up with decent variable names. I don't want to call it M. L, you just want me to use the run L. I'll go. I know.
Mux4_.
Mux4_out. That is actually a really good name. I was just trying to keep them short for the sake of me writing. We'll just go with L. Okay, so L is an out. The other two are ins. I know I'm going to end with parentheses, but notice here how I have S. It's going to be a little bit different because I know I need S0 and S1. Let's introduce a new type. My new type is standard logic vector. This is a vector, right? A one-dimensional array, right? It's just line of values. So I now have S is an input of standard logic vector, then I have to tell it how big it is. It does not like to not know how big something is. And the way I do that is 1 down to 0. The last line is a little bit different. It has a parentheses and then the semicolon. Okay, just pay attention to that. So standard logic vector is, right, you would draw it like this. Right, it's a bus. One line that has 2 bits in it. I can then address any one of those. So this whole thing is S. If I want the first bit, I say I want S at 0. If I want the second bit, I would say S at 1, right? This is just giving the location in that vector. Or I can write S and get both of them. Make sense? Okay. So this guy, for our, we say end lux 4. Notice how much faster I can do this once I have something to reference and just go look at. Get better, you'll get practice at it, it'll start to get familiar. Then we would do the same thing. Architecture. I should do that higher, just so I have room. Architecture. Okay. Now, I have to do one more thing, which is, yes.
Can you leave architecture abbreviated or do you have to take out the word?
It will actually just make it for you. But yes, no, it's just a name. You could literally just put B there and it would be fine. Yes, the architecture has to be the full word. I will just start, I abbreviate things if I'm drawing on the word, like down to, I will eventually switch to 1 down to 0. Okay, now, any idea why I'm doing 1 down to 0? Think about when you write a number. 175. We read and write left to right. My biggest number is the leftmost number. So when I say I want, this is my index 2, index 1, index 0. So because of the way humans think, if I were to write I at 1, right? Because this is a vector, standard logic vector that has 3 bits in it. Well, 3 decimals, but pretend they're bits for the moment, right? I at 1, I would expect 7, right? Well, that's symmetric, everything is fine, no matter what. But if I were to write I at 0, the smallest bit, I would like to have 5, right? If I don't do down to 0, it writes the number the other way, and the bits get bigger the further they go to the right, instead of down to. So down to orients it in a way that you think. You can write it 0 to 1 like that. It doesn't say up to, it just says 2. That's fine, but we'll put the number in the wrong order for you, which is a problem, right? Okay. The next thing I have to do, remind you guys that VHDL, most programming language, don't know things exist until you tell them they exist. I'm going to need to tell it both, because this is the red box I'm going to build, right? I need to tell it a couple of things. I need to tell it that the mux exists, and I need to tell it that these signals that connect them together exist. Because when I create the entity A, B, C, D, S, and L, it makes all of those the connecting signals for me, as well as the ports. These aren't ports, they don't exist yet. Okay, so what I do is I come over here between the architecture. So the architecture is the only thing that cares about what its name is. So between the architecture and its begin, I write signal, right? Just like the entity warns the program that the entity is coming, signal warns it that, hey, I'm about to tell you what my signal, that there is a new signal. It works very similar to the ports. I would write something like M0, M1, colon, and then I just have to give it its data type, which we're going to use as standard logic. Done. Now, I could just as easily, since they're the same type, I could make just an M vector, right? These are just individuals. If I take 2 bits, stick them together, now I have a 2-bit vector just like this guy. Okay, here I'll declare them differently. Now, declaring that the mux exists is a little bit more complicated, but not much. The idea follows the same thing. We start with a keyword that says it exists. Component. I'm about to give you a component. Okay. Now, I have to give this component a name. It turns out in this case, my component name is mux, right? I'm making that connection between this component declaration and the thing I just made. So my component mux is. Guess what? It's going to have ports because I need it to tell it what to expect. So it says port, and I just pull this in, right? XYS, input standard logics. F, output, standard logic. I'm actually doing a pretty good job of sticking to like actual code for now, so. Okay. Now, you don't have to know all of the code exactly. It is good to have the reference notes. I do have pretty decent tutorial videos posted on my YouTube channel that later you can go back and review. But let's focus on the ideas mostly, right? That's what I want you to focus on, because I want you to understand why you do things so that when you have problems, you can think about it from that perspective. Okay, input component mux. And then this time we say, I'm done declaring this component. It's a little bit different, right? Because in the entity, I say entity mux is end mux. Same thing here, end mux for, and the component is end component. Okay, so it's just saying that that component exists. There is a reason for that, but I don't think I want to get into why yet. Yeah, I don't want to get into why yet. Okay, now I have signals that exist. I have components that exist. Yay, right? Okay. Now I can do the begin of my architecture. And I need to tell it, how are they connected? Now, the thing you need to resist is rewriting the mux code, right? There is no reason that I need to program 3 muxes. Okay, because it's the same thing. So I'm just going to tell it exists 3 times. Okay. Now, the way it is going to work, and I'm going to erase this half of the board So hopefully you guys remember what is inside of the mux. It is not very difficult. And I'm going to continue from the begin here, okay? So inside the begin, I need to tell it, one, how many of these things that I want, right? So it knows that I have component mux, but because it's digital, it's theoretical at the moment, I have an infinite number of them just laying around waiting to be used. It's like that little bin, I can pull it out and pull them in, but I just have to give them a name. So like when you're drawing the schematics, we would like call them U1, U2, right? To give them the designator name. This is the same kind of thing. We're going to give these components designator names, right? And we can call them, and again, we can look back and I made a bad decision. And if I was more willing, I would go back and change M, because I feel like M0, M1 is a good name for the muxes. But there, and then I don't want to name it mux4 because I don't want to give it mux with a number because then that might get confusing. So I'm going to go with standard designator names. I'm going to give it a name, U0. Okay, and then once I do that, I have to tell what am I naming that? Well, I'm naming mux. Remember, I called these components muxes. Mux. That's what this component is. So I have a component of a mux named U0. Now I need to tell it how those ports are connected. Okay, and that's just as simple as giving it what is called a port map. This is how the ports are mapped. Where do they go, right? This port map is a description of where the ports go. Now, there are two different ways that you're going to see these ports written. I don't recall which way the book does it. I'm going to do it what's called explicitly, okay? Shoot. I may screw this up. I don't have an example pulled up, but I'm going to try. Okay, so I know that it has ports X, Y, S, and F. Okay. Now I write this. Port X is getting mapped to something. Okay. Well, what is U0? So let's go ahead and name them so we know which ones I'm talking about. U0, U1, U2. Okay. So I've named this guy U0. That means my X port is connected to the bigger port A. A. This is a comment. This whole thing can be written on one line. It works just fine, but it's a little bit easier to map out. Y, similarly, for the same reason, it's mapped to B. F, similar, well, let's do S. I was going to speak F for a reason, but let's do S. What is S getting mapped to? In my diagram. Yeah, S0, right? This S0 is getting plugged into this S and that S. So I say S at 0. Now, I did this on purpose. See how this S and that S are the same letter, but they're different ports, right? This S refers to that S, and the S at 0 refers to that S, and this S is the port that's inside the mux. So this is kind of bad. I wanted to show you why you need to be careful with your port names. Okay, let's go back and rename it. See the space I gave it? Cell. SEL. Select turns out to be a reserved word, so cell for select. Now, when I write this, cell at 0, right? Because cell is my 2-bit vector. Now it's getting mapped. That makes sense, right? So this is how we access 1 bit of that select signal. F. Because it wouldn't make sense to try and take two wires and plug them both into the S port at the same time, right? Imagine them like a headphone jack. If I have two headphone jacks, I can't stick 2 bits into one port. I have to pick one. This is how I pick one. Right? Okay. F finally, we called M0. I've said M0 exists. I simply write M0.
So when you just renamed that to SEL set, right behind you, that could be, yeah, that way.
Yeah, so this, I'm gonna write it outside so I can write it big, but remember that this is the port. Cell 0, cell 1. Okay. Cell at 0, cell at 1. There is one port called cell. So I can go ahead and further modify this to represent that fact. Notice that this looks like 2 inputs, but it's going to really be /2. That makes it a bus. /1, /1. Right? Now this is indicating that I have split my bus. Okay, I have a 2-bit cell port that I split to go to 2 different directions. Okay. Where this is cell at 0, this is cell at 1. You may want to write it so that it's clear if you were designing your own. Now, I want to be very clear. In digital design, draw pictures. Draw a lot of pictures. I design very little without drawing some form of picture, because this is your biggest clue to make sure this is your reference, this is your map, this is your guide into turning your idea into code. It is very difficult, especially beginning, to make code without a map, right? So build your plan, execute your plan, right? So generally, we can now go back and reflect on what I've done so far. We generally conceptualize an idea from the top down, okay? We call it top-down design or top-down conceptualization. My top-level idea is I need a 4-bit mux. Okay, how can I make that? Well, I knew that I could do that with 3 2-input muxes, right? And then I went in and I designed. When I actually started designing, I designed bottom up, right? I built my first mux first, and then I connected them together. So we design bottom up, we conceptualize top down. I highly recommend designing it that way. Okay. Now, this is done. I've made a mux. It has maps. It has these connected to these wires. Everything's fine. Okay. U1 is also a mux. It's the same, right? I'm reusing code. We call that code reuse. Super fancy, right? It too has his own port map. And this is the other way of writing port maps. This is the worst way of writing port maps. You will do it, but you shouldn't. The reason you will do it is because it is shorter. This is an explicit port map. This one is going to be an ordered port map. So the cool thing about the explicit is it does not matter the order in which I assign the ports. And I do not need to even assign all of the ports. Ordered port map, neither of those is true. So the first thing that I put is X, which is mapped to C. The next thing that I put is Y, it's mapped to D. The next thing that I put is my select signal, cell at 1, and the last thing that I put is mapped to F.
And, it's not based on the order up there, it's the order in the.
Right, but you should always, this should always be the same, by the way, your component declaration, not because it's strictly enforced, but because if you're typing this whole thing out, you're wasting time because you can go to the entity, copy, paste the entity, you change the word entity to component and add the word end component instead of end entity name, right? Then you copy and paste it, there is no room for errors in your code. Right? Copy and pasting prevents you from making a typo here and saving me from spending 15 minutes debugging with you because I don't see the difference between like there and there, right? THDIR versus IER. People, you will make that frequently. Everyone will do this at least once, probably this semester, where they'll type a port name and they'll flip 2 letters just because they got going fast. And those are very difficult to hunt down. So the copy paste saves you from doing that. Okay. U2. Still a mux. Still needs a port map. This one is a little bit different, same idea. What do you think I plug into my first slot? Yep, 0. Next slot. Yep. And I think you guys got that from now. So I select, oops, I made a mistake, right? Select 0. This is select 0 as well. These first 2 need the same signal. So that was a mistake. That's okay. This one takes select 1. If you make this typo, eventually next time we will teach you how to design simulations to solve that problem. Well, to find the problem, moreover. And then its final output is L, right? Because I want this guy connected to my output. This is my structural code. I built one bus. I created 3 instances of it. So component declaration, component instantiation. This is an instance of this. So in the wildlife, you have a component called deer. The deer makes a baby, you now have a new instance of a deer, right? That's how it works. Okay. The way I name these, tell them how they're connected, I'm done. I now have a 4-input mux built out of 3 2-input muxes. That's Vivado.
You have to like put it in.
Yes, yeah. You will have to go and say, and behave. So the things that we've learned, how to make little modules, how to combine those modules into a bigger module. Oftentimes I will refer to that bigger module as a top level module. You will be inclined, because design education talks about this way, is calling that top. However, I recommend against ever calling anything top, because what happens when you want to stick Mux 4 into a bigger project, right? I knew this was going to be my top level module for this project, so I could have called it top. That's a bad name because I'm going to use that in some other thing, and maybe that's going to be called top 2. Like, what am I? That's crazy, right? Choose good names. It will save you a whole lot of time. Okay. Now, I do still have 15 minutes, so I can go ahead and give you guys an introduction to Vivado. Maybe. Not sure on the camera. Great. Okay, so this is Vivado. VHDL is a standalone kind of language, right? This is going to be your design environment. Something that I like to say about it is you do not have to write your code in Vivado. You guys will probably want to start out that way. But when I was in the industry, so I did this for years in the industry, and when I was doing stuff that I was spending a lot of time in digital design and building systems, staring at a white screen with black text gave me like a near permanent eye twitch because of eye fatigue, which was awful. So I use, and there are better tools than this, but I'm kind of a minimalist. This is a program called Notepad++. I imported this is really hard to see, I know, but don't worry about it. A way to turn this light off in the front. I don't think it's divided, unfortunately. Sometimes these classrooms have a special thing, but I can reduce the lights at the very least, I think. Come on. Nope. There is a way. I don't know, but you've seen I've been technologically cursed for a while, so I don't know what's happening this semester. Anyways, I downloaded a special thing that's called Solarized Dark. There's Solarized and Solarized Dark. So the Solarized and Solarized Dark is a color scheme designed by neuroscientists to specifically minimize eye strain. So you may want to do that. But the thing about Notepad++ is it doesn't have any of the tools that kind of hint at you what you've done wrong. It is a very minimal design environment. Okay, when you meet Vivado, it's going to pop up with something like this. You're going to need to create a new project. So we'll go File, Project, New. It's going to create this little wizard for you that you can walk through, that give it a name. I'm going to call it something descriptive, ECE2700, FA21, intro. There we go. That's probably a good name, right? Now I know when I did this, I know what it is, so that I can go delete it later. All right. Sources. Your sources are any modules that you want to use. So see how this says add sources? You can add them here. Ironically, I highly recommend you don't do that. The reason is really stupid. If I have one module, it spews it out with like a whole bunch of code that is helpful and ready for you to use. If you make two, the second, third, fourth onward doesn't have any of that useful starting points. There might be a way around it. I don't know it yet. You want to make sure down here on the left that your language is VHDL. Verilog is the other super popular language, but we use VHDL. Constraints I'll get to later. This is the part, what device am I programming? You don't need to worry about that just yet, so you can hit next on any of them and hit finish. All right, this is your main project type window, okay? What you can do here is things like add sources. You see where my mouse is here? See that plus button? If I click that one, this is my add sources. Design sources is your main thing, right? The MUX, the MUX4, all of that is going to be a design source, okay? Constraints files we'll get into later, and simulation is kind of obvious, right? It's a file to tell it how to simulate. Let's start with design sources. Now, this is where I tell it whether am I pulling in an old design source, right? If I've already designed a MUX, I could just go pull that in from somewhere else. I'm going to create a new one, so I'm going to click this create file button.
And I'm going to call it mux. No surprise there. I hit OK. And I'm going to hit finish. That window has the same problem. If I create more than one at a time, for some reason, the other ones don't have all the useful bits. This window, define module, allows you to enter your ports. You can do that here. I never do. I just click OK. Yes. That brings us to the sources window in this kind of top left area. Sources are where we go to look to see what our sources are. See how there's a mux? This is not very different from any file browser. You double click on it, it will open mux. I have made my font ridiculously huge so that you guys can read it. Now, it throws in all of this stuff at the beginning because it's just good practice to use, like to say who it is, blah, blah, blah. I'm going to do the very responsible thing and delete it all to start with. The next thing, see how this says library IEEE and then use IEEE standard logic? Libraries, if you use any other programming language, you're probably familiar with libraries. It is a grouping of tools that you can use so that you don't have to program everything yourself. This library in particular is very useful because it allows you to use standard logics instead of just bits. I avoid using bits anytime I can because they're a nightmare. Standard logic is much easier to work with for a number of reasons. So we like standard logic. I also highly recommend uncommenting. So just deleting, so dash dash makes it a comment. If you don't know what a comment is, it's saying that this line of code is only to describe what's happening. You'll want to comment your code so that when you go back and look at it later, you know what it's supposed to do. I'm going to delete those comments because I know that this one imports a thing called numeric standard. Now, your book is going to tell you, I think, to import something called signed or unsigned, maybe. If it does, I'm hoping we updated that. If it does, don't. Because signed and unsigned are traps. They're not actually real IEEE approved libraries. Now, IEEE, in addition to being the club that I'm the advisor of, is also an industry standards group. They kind of communicate how do you make things talk to each other nicely. If you use signed or unsigned libraries instead of the numeric standard, they're not really official, and so they may not work on all hardware. This is supposed to work on virtually all hardware. It's a universal standard. Okay, this Unisim stuff, you can just delete it out because we don't need it yet. You will eventually, but not yet. And notice now, it has created all sorts of useful stuff for me. It has created the entity and suggested that maybe I want some ports in it. It has created the architecture and given it the default name of behavioral. It has given me a begin and an end with some space between architecture and begin to remind me that maybe I need to put some declarations, whether they're signal or component declarations, right? This looking very familiar to what I wrote on the board. So I want that mux. Uncomment the port. I called them X, Y, and S, right? Those are my inputs. Give it a type in, and they are standard logic. Semicolon return. You don't have to return. I highly recommend doing it. F is my output, says out, and it is also standard logic. It exists, right? Super easy. I know you'll forget, but don't really do this a lot in lab. I don't need to declare any signals because all of the signals that I'm going to use are my ports, right? So then my begin, remember I said I need to assign my outputs, any and all outputs I want to assign a value for, because if I don't assign a value, they're, I don't know, and that can cause problems. And then I need to say, what is F? Well, it is X when S equals 0, else Y. No error lines underneath it. Everything is fine. If I have an error, so say I type Z, puts a little error line over it, right under it. I mean, if I put my mouse over it, this is very hard to see, but it says error Z is not declared. It doesn't know that it exists. Notice that this is a little z, I wrote a big Z, it's because VHDL is not case sensitive. Be careful with that, because you can't declare something little z and then something else big Z, they'll be the same signal. So Z is not helpful, I'm gonna make it Y. Control S saves it, I have now designed a mux. Now, if I need a new component, I can pop open my sources window and hit that plus button again. I'm going to go ahead and create a new design source. I have to create a new file because I haven't built it yet. I'm going to call this one mux4, just like I did up on the board. Hit finish. It's going to suggest me to make ports. I'm not going to do it that way because it actually takes longer than typing them out like I showed you there, right? It actually takes longer to use that window. I double click on it. I delete the stuff that I don't really care about. I uncomment IEEE. All the stuff is up there. I'm not going to uncomment it so that I can get this done in 3 minutes. The ports are A, B, C, D. I don't actually need these spaces. Yep. They are ins and they are standard logic. I then have S, which is an in, which is a standard logic vector of 1 down to 0. And then I need my out, which we decided to call L, which is an output of standard logic. No error bars, everything's fine. If you do encounter an error bar, you always need to go, it's usually on the line that the error is or the line above it. That's not always true, but that's why you look. Is it error bar is not always the line that it's under. It could be caused by something else, okay? I need to declare my component. So I go inside of the architecture, but before it's begin, right? And I would just write the word component. Well, let's not do that. I could write the word component, or I can be smart and go to this entity, Control C copies, go here, Control V pastes. I just change the word entity to component and then say end component. Only 2 changes required. I now have a mux. If I wanted to go make that mux, I called it. I'm almost out of time. So I'm going to name it U0 in order to make a mux. When I make the mux, I need to tell it is a mux with a port map. I'm just going to go ahead and do an ordered assignment so that I'm going to have A, B, select is S. Did I call it cell responsibly or did I call it S? Let's rename it cell. Cell at 0, comma, M0 parentheses. Okay, it's going to be unhappy because I don't have an M0, right? So when I realize that I don't have an M0, I can jump back up to this signal, M0, standard logic. It's pretty standard to just make things as you need them, right? I've now declared my mux. I could go on, make the remainder, everything's fine. Okay, that's VHDL. Now, that's strictly combinational VHDL. Next time we'll get to sequential VHDL, things with memories, and I'll also introduce how do I test this. Okay. Copy paste is your friend always, like this U0. I can literally just Control C, Control V, and I have most of the code right. It's now U1. I just have to change the ports. Anyways, that's my time. You guys are free to go.
So for the lab, we need to have anything downloaded on our laptops or anything.
Oh, I will post. You do not need them. It is all installed on the hardware in the lab that we use. You can install Vivado. It is free to use. If you want to do that, wait until I post a thing that kind of walks you through the instructions, because Vivado is huge. If you do it wrong, it's like 60 gigabytes. If you do it right, it's 20 gigabytes. So it is a massive program. So wait until I post the how-to to make sure you don't fill up your entire hard drive. There is, and I'll try to remember, an online editor that you can actually use for most of it.
I'll probably download it.